Hello everyone, we are Group 21 and today we are going to introduce our work to you, named Prompt Engineering for LLMs in Cost-Effective Math Reasoning Tasks. Here is our group's presentation agenda. Before we start to talk about our methodology and experimental results, we will introduce you to some background information and our motivation. To do that, let's first answer the following questions. So for the first question, in short, a large language model's math reasoning ability is generally measured by its capacity to tackle difficult or novel math problems with abstract concept understanding and novel thinking. For the second one, prompt engineering is a key parameter fit strategy to enhance LLM's abilities in, but not limited to, mathematical reasoning tasks. And finally, our motivation is to unlock the math reasoning abilities of small language models. In other words, given a math reasoning task, if a small model can do very well, there is no reason to use a large one. And next, we will introduce you to our methodology to achieve this goal.
Firstly, we choose a wide range of models, including GPT, Qianwen, ChatGLM, DeepSeek, Doubao, GM4, and eSpark, which together contribute to 10 models in total. Secondly, we choose a GSM-AK as a dataset to benchmark the model's math reasoning abilities. And then we used 4 different prompting strategies to test the model's mathematical abilities. The first is zero-shot prompting, which means we directly ask the models without any explanations or examples. The second is few-shot prompting, which is provide several examples in the prompt to the model for in-context learning. The third is chain-of-thought prompting, which is use reasoning instructions to force the model to output the reasoning process before giving the final answer. And the last one is chain-of-thought with few-shot prompting, which is combine both examples and explicit reasoning instructions to the model. Finally, we use accuracy, BLUE, and rouge metrics to do the overall evaluation. Next are the experiment results.
This slide shows the average cost versus average accuracy for different models under zero-shot settings. This slide shows the distribution of pop token counts across different models under zero-shot settings. This table shows the accuracy metrics of each model under zero-shot and few-shot prompting strategies. And this table shows the accuracy matrix of each model and the chain-of-thought and the chain-of-thought with few-shot prompting strategies. Here you can see the bar charts showing the ratio of pop tokens to completion tokens under different prompting strategies. It's important to note that the pop tokens in each figures are equal, which means the content set to the model is consistent. And a larger yellow proportion means the model generates more response. As you can see in the comparison graph, the chain-of-thought methods present a positive contribution to increase the final accuracy for all models, while the few-shot methods had limited contributions. Here you can see the quantified performance improvement among different prompting methods, and it's notable that the chain-of-thought methods can even boost the accuracy up to 78%. Finally, you can see that after applying our prompting engineering methods, the number of correct questions significantly increased compared to zero-shot methods. And thus, we can summarize the following 4 conclusions. Chain-of-thought is the most cost-effective strategy for small and mid-sized models. Chain-of-thought with few-shot methods is expensive and offers limited improvement. Lightweight model can achieve great performance with the chain-of-thought at a low cost. GPT-5 is powerful, and it's hard to show the effectiveness of prompt engineering strategies for moderately difficult tasks. And here is the future improvement we can do next. Anyway, thank you for listening.